who thus became an assistant professor after being Dr. Eric Rowland for 6 years.
6.5.
Yeah, 6.5. He got his PhD at Rutgers, so it's nice to have him back. And he's going to talk about computer verification of integer sequences, avoiding a pattern, one of my favorite topics, and by the courses. One of them is also one of my favorite people, the other one I won't mention. And if that's to join us for dinner, please let me know immediately after the talk. You're welcome to come. It's the usual place, Evelyn, at 6:45, but I need to know when they will come. Thank you.
So, thank you very much, and thanks all for coming. I lost my voice a couple weeks ago. Sort of a combination of teaching and getting a cold, but I think it'll last for an hour. So yeah, this is joint work with Jeff Shallett and Laura Pudwell, not together, but in 2 separate papers actually. So that's why they're in that order. And it's kind of a nice topic. There's a mixture of some combinatorics and some number theory, and a very healthy dose of computer experimentation and then theorem proving using a computer. All right, so what's the main setup? Periodic sequences are very simple, right? They're sort of the simplest kinds of sequences that we can imagine. You can compute the nth term very quickly. You know, I mean, there's not much to say about them. They're that simple. So if you want to sort of step up in the sort of hierarchy of integer sequences, or in this sort of hierarchy of complexity, we could ask, here are 2 natural questions. And they're sort of vague questions, but they're maybe worth thinking about. The first question is, what are the simplest non-periodic sequences? Right? And of course it depends what you mean by simple, and so many people might have different ideas about what they mean by simple. So I'm not going to answer, I mean I have some ideas about this, but this isn't the main question in the talk. Instead of trying to maximize simplicity, what I'm going to try to maximize is non-periodicity. So it's really the second question that I'm going to be interested in. And so that's how non-periodic can a sequence be. So how far away can we get from these very simple periodic sequences? So here's the starting position. A square is a non-empty word of the form WW. So it's just a block repeated by itself. And I'm going to distinguish words from sequences. Just for convenience, words are going to be finite, sequences are going to be infinite. But otherwise, you could talk about infinite words or finite sequences, but that's just the terminology.
And the alphabet is finite?
Not necessarily. So initially we'll start with the finite alphabet.
Wait, so they're not just numbers?
No, a word, so it's a sequence, yeah. So the word might be 0, 1, 1.
Okay, so but a word is necessarily a finite sequence of digits.
Right.
Okay.
Yeah. So this is Axel Thue, who is a Norwegian mathematician, and he started asking questions like the following about 100 years ago, and this was really the birth of a field that's now called combinatorics on words. So one of the questions he asked is the following: are squares, meaning repeated blocks, avoidable on a 2-letter alphabet? So this is equivalent to saying, are there arbitrarily long square-free words, on the alphabet 0, 1, right? Because if they're arbitrarily long square-free words, then we can build an infinite one, sort of pretty easily. So, maybe you don't know the answer to this question, and you'd like to know the answer. So what we can do is choose an order on 0, 1. Let's say 0 is less than 1. It's a good order, and we try to construct one. So we always write down the lowest number we can, the lowest term we can, and trying always to avoid squares. Okay, so we first start by writing a 0. So this is a square-free word so far. It's square-free, so that's good. We can't write a 0 next, right? So we have to write a 1, right? Because 0, 0 would be a square. What happens next? We can't write a 1 because 1, 1 would be a square, so we have to write a 0. And then what? We can't write a 0 because 0, 0 is a square, but we also can't write a 1 because 0, 1, 0, 1 is a square. So the answer to this question is no. A word of length 3 is as long as you can get on a binary alphabet. if you want your word to be square free. So maybe you think, well, maybe, at this, when we were doing this, there were no choices, right? At every point, well, we started with a 0. We could have started with a 1, but of course it's the same no matter what you start with. So this is a pretty easy proof that the answer to this question is no. So what about on a 3-letter alphabet? So now we have 3 letters, 0, 1, and 2. And we can play the same game. All right. So we write down a 0. We can't write a 0 down. We can write a 1. So now we started off just as before, right? Because we're using the smallest number we can in every step. But now we can write a 2, because we've never seen a 2 before, so we're certainly not going to introduce a square by writing a 2. Now what? We can put a 0 again, I think. Right? We can't put a 0, but we can put a 1. We can put a 0 next, because that one, so now you have to check, right? And it takes a little longer to check, but if you can check that if you put a 0, you still don't have any squares. Now we can't put a 0, we can't put a 1, because 0, 1, 0, 1, but we also can't put a 2, because 0, 1, 0, 2, 0, 1, 0, 2 is a square. So it looks like we're out of luck. But we didn't exhaust all the possibilities. Maybe one of our choices previously was not a good choice. So now what we do is we say, okay, this 0 that we just put down on the previous step, maybe that was a bad idea. So let's go back and change that to we can't put a 1 there, but we can put a 2 there, and that's what we've done. I'll show you the transition. So that's what we had before. So we're deleting that 0 and replacing it with a 2, and now we're fine. And so you can keep going, and you build this long word. So this is the lexicographically least word that avoids squares, right? Because we're always putting down the lowest letter we can, and if we get to a point where we run into a problem and no letter will work, we just backtrack. And this is a good way to sort of get intuition about whether a certain pattern is avoidable on a certain alphabet. You just try to build a lexicographically least word that avoids that pattern and see if you can get a really long one. So 2A in 1906 proved that there exist arbitrarily long square free words on a 3-letter alphabet. This isn't the word that he, so he proved this theorem by exhibiting such a word. This isn't the word that he exhibited, but he exhibited a word that's related to the 2A Morse sequence, if you know what that is. But this is true. I'm not going to go through the proof of this, but it was, this is one of the first results in combinatorics on words. And the backtracking algorithm that we've been doing builds the lexicographically least sequence that avoids the pattern. So here's an open problem. Characterize this sequence. Of course, what do you mean by characterize? Of course, it already has a characterization as the lexicographically least square free sequence on 3 letters. But I think the idea is, can you say anything about the structure of the sequence? Can you compute the nth term in a time that's faster than just writing out, starting from the beginning and running the backtracking algorithm? So this is an open question. So
or maybe get a similar construction to the original.
Right. Or maybe get some other construction. Yeah.
Right. So look it up in the OEI.
We can look it up in the OES. I think we wouldn't find any other characterizations in the OES, but I could be wrong. Yeah. So this book was published, I don't know, 10 or 15 years ago. So maybe someone has worked on this since then. But I think the structure of this word is still unknown. So on a finite alphabet, this happens a lot. If you're writing down the lexicographically least sequence that avoids a pattern, most of the time, in my experience, you can't say, it's difficult, or at least no one knows what the structure of the sequence is. Okay. But on an infinite alphabet, things are very different. So on an infinite alphabet, for one thing, the backtracking algorithm doesn't actually backtrack, right? Why is that? Well, because there's always a number that you haven't used, right? So you can always stick in a number that you haven't used yet. So you never have to backtrack. So that's really nice. When you compute a prefix, when you compute one of these, like you compute the first 100 terms in one of these sequences, it's actually it's actually a prefix of the full lexicographically least sequence, because you're never going to backtrack into that portion. So are squares avoidable on the alphabet of non-negative integers? Yeah, right. So the sequence, do I have chalk here? So the sequence, I mean, for sort of silly reasons, right? The sequence 0, 1, 2, 3, 4, 5. Right. This is a square-free sequence. So the answer is trivially yes. So then we can ask about the lexicographically least square-free sequence on integers. So let's start building it again. So we have a 0. We can put a 1. We can put a 0. We can put a 2. Right. So at this point, we're still this so far it agrees with the lexicographic.
But also square that avoidable and 0, 1, 2 with a subset.
Right.
Of 0, 1, 2.
Right. But we may not get the same word because we won't backtrack. So right here, we will write a 3 instead of having to backtrack at that point. Okay. So this is a nice sequence. It's called the ruler sequence. The nth term is also the two-adic valuation of n, meaning if you write the prime factorization of n, it's the exponent of the prime 2. Right. So every odd number is divisible by 2 0 times. Every number that's congruent to 2 mod 4 is divisible by 2 once. Every number that's congruent to 4 mod 8 is divisible by 2 twice, etc. So this is a really nice sequence. Mathieu Paquet and Jeff Shallot in 2009 wrote a paper. This wasn't the main focus of the paper, but this was included in the paper sort of as a warm-up example. The lexicographically least, so this sequence, the lexicographically least square-free sequence on non-negative integers, is not only this ruler sequence, but it's also generated by this morphism. So what do I mean by this morphism? So this is a morphism on, it's just on the the free semi-group, if that means something to you. If it doesn't, it's just it's just words. So for every we have infinitely many letters now in this alphabet, right? Every non-negative integer is a letter. So we have to say what happens to every non-negative integer. And what phi does is it turns n into 0 followed by n plus 1. Right? So phi of 0 is 0, 1. And then to compute phi squared, we apply phi to that, right? So 0 becomes 0, 1, and 1 becomes 0, 2. And then this is phi cubed. And it turns out that if you apply this morphism, if you keep applying this morphism, what you get at every step is an extension of the thing that you had on the previous step. And so in the limit, you get this infinite sequence. This is a fixed point of the morphism, actually. So if you apply phi to this infinite sequence, you get this infinite sequence back. So this is just a different way of thinking about the structure of this word. It's a morphism characterization. And throughout the rest of the talk, these morphism characterizations are going to be the main way I'm going to be writing these results. They seem to be the most natural. Well, one of the most natural ways. Okay, so that was the lexicographically least square-free word on the non-negative integers. So what about other powers? So let a be some integer greater than or equal to 2. And it turns out that the lexicographically least a power-free word, so cube-free word or fourth power-free word, also is given by a very similar morphism, where instead of just 0 followed by n plus 1, we have a minus 1 zeros followed by n plus 1. So here's the lexicographically least fifth power free sequence, for example. And it's a fixed point of this morphism that just sends n to 0 to the a minus 1 with an n plus 1 on the end. Right? So for sequences like this, and by the way, this sequence is the 5-adic valuation of the integers. So it's slightly easier to see the structure if we wrap this sequence, into lines of length 5. And I'm going to do something else, which is now to represent this wrapped sequence graphically as an array of cells, where 0 is a white cell, and 1s are going to be rendered by gray cells, and 2s are going to be rendered by slightly darker gray cells, etc. So we only have 3 numbers in this particular prefix. Of course, we'll get more numbers as we go on. But you can kind of see the structure here. We have 4 columns that are all white, and then this last column, what do we have actually? If you look at the sequence here, we have 1, 1, 1, 1, 2, 1. It turns out that sequence is the original sequence just shifted up by 1. right? Which makes sense if it's if you think about it in terms of divisibility by 5, right? If you take every multiple of 5 and divide them by 5, then you'll get the original sequence of integers back. So here's a recurrence for this sequence. We have 4 columns of zeros, and then this last column is the original, a term in the original sequence incremented by 1. And this recurrence sort of reflects the base 5 representation of n, right? If I want to evaluate s of n for some n, basically I look at the last digit in base 5, and that tells me which of the 5 cases to apply. And this is an example of a 5 regular sequence. So it's, I'll give the definition a little bit later. I don't want to go into it quite yet because I want to show you some more examples. But basically you can think of 5 regular as reflecting the base 5 representation. All right, so integer powers are easy. We sort of know everything about them. So, all right, now is the previous slide. The lexicographically a power-free word is a fixed point of this morphism, and that's it. So, to make things interesting, we're going to look at fractional powers, and things get very interesting because we know, well, through a lot of work, we were able to figure out some things about this situation, but definitely not everything. So, what's a fractional power? A fractional power is like a partial repetition. So a 3/2 power, if you have a word that has length that's divisible by 2, the idea is that a 3/2 power is, you would write that word twice, but sort of chop off the last half of the last word. Right? So you take 1 1/2, you take the word and then the first half of the word. That's a 3/2 power. Right, so 0 1 1 1 0 1 is 0 1 1 1 raised to the 3/2. Because it's 0 1 1 1 followed by the first half of that word. Similarly, if you have 3 words x, y, and z that have the same length, then the word x, y, z, x is a 7/3 power. It's a square. It's x, y, z, and then the first third of the original word. So here's the formal definition. A word is an a over b power if you can write it as v to the e times x, where x is a prefix of v, and the lengths of v and w are related in the right way. I find the examples easier to understand, so but whatever's easier for you. This is the definition. All right. So the main object of the talk is this sequence. S sub a over b is going to be the lexicographically least a over b power-free sequence on the non-negative integers. And we assume that a over b is greater than 1 because, if a over b is less than 1, if you're trying to avoid half powers, what's a 1/2 power? Well, everything is a 1/2 power because you can always, write it as it's half of something, right? Yeah.
So does being a over b power-free preclude having a higher power or some other fraction?
No.
And when you say that, what are you precluding that in your definition or no?
Yeah. So this is. I just mean this avoids a over b powers.
Okay.
It might. So just because you avoid a over b powers doesn't mean you avoid powers that are greater than that.
Yeah.
Thanks. And so we're going to assume A and B are relatively prime from now on because why not? So S of 3/2. So this is we're going to play this game one last time where we go term by term. So we can put a 0 next, right? So that's a square, and squares are larger than 3/2 powers, but this is still not a 3/2 power, right? So there's an alternate definition where we would avoid everything greater than or equal to 3/2 powers, and you can look at that. I mean, we did look at that a little bit. It seems to be more complicated, so you seem to get structure less often, which is why we're focusing on just avoiding 3/2 powers, and that's it. So we can't put a 0 next, right? So 3/2 powers, they look like 3/2 powers look like x, y, x, where x and y have the same length, right? So it sort of doesn't matter what y is. We just have x followed by x with something in between them that has the same length as x. That's a 3/2 power. So we can't put a 0 next because cubes are 3/2 powers, right? but we can put a 1. We can't put a 0 next because 0, 1, 0 is a 3 halves power. But we can put a 1 next. So what's next? Now we can put a 0, I think. We can put a 0 again. No, we can't. Oh yeah, because 0, 0, 1, 1, 0, 0 would be a 3 halves power. We also can't put a 1 because 1, 0, 1 is a 3 halves power, but a 2 works. Right, if we haven't seen a 2 before, we can always add a 2 because it won't introduce any 3 halves powers. Now, we can't put a 0 because 0, 2, 0 is a 3 halves power. We can't put a 1. No, it gets more big. So what about
0?
We could put a 0 next. We can't. Can we put a 0 next? I think 0 might work. And then a 1.
It's gotta be. Why wouldn't it work?
Why wouldn't it work?
Oh, why didn't it?
So let's see. Why doesn't 0? Why isn't 0? Work?
Because the whole thing.
The whole.
Wait, no. Something like that. Yeah, 0, 0, 1, 1.
No,
No.
it can't involve the 2.
But the 2 could be in the middle.
Yeah, the 2 could be in the y.
Oh, yeah.
Yeah. So 0, 0,
Yeah.
1, 0.
Yeah, 0, 1, 1, 0.
No, that doesn't work. What? 0, 0.
Oh, yeah.
Anyway, when you do it with a computer, the computer doesn't. The computer just checks
1,
it.
1, 0, 2, 1, 0. No. Maybe you should do that.
Let's see.
How about 1, 0, 0, 1, 1, 0?
1. Oh yeah, there we go.
Yeah.
1, 0, 0. Thank you. 1, 0, 0. Right. So 1, 0, 0, 1 is y. And
Aha.
Thank you. Yeah.
You're
And
a
1
hero.
can't work because 1, 1, 1 is a cube. So all right. So you get another 2. If you go a couple more steps, you get a 3. Yeah, and eventually you get a 4. So what's the structure of this word? So in the paper with Jeff Shallett, this is one of the things that we looked at, the structure of this word. Does anyone see any useful patterns or regularities?
0, 0, 1, 1 seems to have
Yeah,
I agree.
0, 0, 0, 1, 1 here appears here, and then it appears here. It appears here.
Basically, immediately after the 2, then not by after the 3, then after right after the other 3.
Yeah, so
And the country is like a 2.
Right.
that seems like a unit.
So it turns out that the right number to sort of break the lines at is 6. If we break the lines at 6, what do we get? So it turns out instead of just, we had columns of zeros before, we don't get just columns of zeros, but at least they're periodic with period 2. So we sort of have a 0, 0, 1, 1, 0, and then on the next line we have 1, 0, 0, 1, 1, and then we go back to 0, 0, 1, 1, 0, etc. And then in this last column, what do we get?
The sequence plus 2?
We get the original sequence incremented by 2.
Have you been a good boy and put all of these into the OEI score? Or do I have to take notes?
No, I will do it. It's on my list. This one might be there
I've
already.
heard that before.
This one might be there already because it's from a paper. Also, it's from a paper in 2012. But if it's not, I will add it. But yeah, there are a lot of these.
And more.
All right, I will. So this is a recurrence. So this is part of the recurrence that this satisfies. And this sequence reflects the base 6 representation of n, right? So whenever we have a 5 and the base 6 representation of the least significant digit, that's when we sort of recurse back to an earlier term. So this is an example of a 6 regular sequence. This was basically the subject of that paper. It took a while to prove. It was sort of a case analysis. How do you prove one of these things? Well, you have to show that at every step, basically, you can't put anything lower than what you claim, and that you can put what you claim, right? So there's 2 steps. You have to show that what you conjecture the sequence to be is actually 3 halves power free, and that it's the lexicographically least 3 halves power free word.
And this was done by computer, I hope.
No, this was done by hand.
Ah.
Well, okay, I cheated. So it was done by hand. The paper was submitted. and the referee said you really need to show more details. So then to show the details, I wrote a computer program to like spit out these like I don't know 20 symbolic identities instead of checking them by hand to appease the referee. But the rest of it was done. But after this paper, I mean it'll become very clear that we need to start using a computer. So my question was why 6? Why, so if you're avoiding fifth powers, it sort of feels right that, you have to look at the base 5 representation of n. But if you're avoiding 3 half powers, why is it the base 6 representation of n and not some other number?
3 times 2.
Yeah, 3 times 2. So that, is it 3 times 2 or, so it's not 3 times 2. It'd be really nice if it were just 3 times 2. I wouldn't be giving a talk then, I think. So I want to give you the formal definition of a k-regular sequence and just talk about this for one slide. So an integer sequence is k-regular if this set of sequences is contained in a finite-dimensional vector space over Q. So and this set of sequences is, so we fix, k is fixed, so we basically take subsequences that are of this form, s of some power of k times n plus some, remainder, where the remainder is, less than k to the e minus 1. So, and I think of these as analogous to things like the Fibonacci sequence. So the Fibonacci sequence satisfies, the recurrence f of n plus 2 equals f of n plus f of n plus 1. And that's equivalent to saying that this set of sequences where we just have a sort of a simple shift in here is contained in a finite dimensional vector space, because as soon as you get past shifting by 2, you can rewrite that sequence as a linear combination of previous sequences. So I think, in my view, these are sort of similar. It's just that instead of shifting in the simple way, which is you can sort of think in base 1, you're sort of sticking R1s at the end of the base 1 representation of n. Here you're just sticking R at the base k, at the end of the base k representation of n. All right. So that's sort of my own take on this. But one thing that's important is to ask whether this value of k is unique, because maybe on the previous slide the lexicographically these 3 halves power sequence could also be 10 regular, and maybe it also reflects the base 10 digits of n. And it's not unique actually. 2 regular sequence is also 4 regular, because you can imagine sort of if you're working in base 2, it's not base 4 isn't too far away, and vice versa. So it's not unique actually, but it's basically unique. So if k and l are multiplicatively independent, which means that there's no powers of them that you can make equal. So 2 and 4 are multiplicatively dependent. 6 and 36, are also multiplicatively dependent. But if you have 2 numbers that are multiplicatively independent, and you have some sequence that is both k regular and l regular, then basically your sequence is very simple. So it's very restricted. The generating function has to be the power series of a rational function whose poles are roots of unity. So this is a pretty restricted class of sequences. So basically, if you can show that whatever sequences you're looking at are not power series whose of rational functions whose poles are roots of unity, then you know that there's basically a unique k up to sort of taking powers.
So it's not a quasi-polynomial?
So quasi-polynomials are k regular for every k. Yeah. So this was proved by Jason Bell in 2006, and it really says that this value of k, it's important. It gives you important structural information because it's basically unique. All right, let's look at some more examples. So what about 5 halves? That's another simple rational number. So here's the lexicographically least 5 halves power-free word. And you might recognize this word because it's also the lexicographically least 5th power-free word.
Oh.
All right, and this is actually a theorem.
Oh.
So if your rational number is greater than or equal to 2, then we already know the answer to this question. We already know the structure of the lexicographically least A over B power-free word. And I should say, at this point, from this point on, all the results are from my paper with Laura, so I'm not going to attribute them every time. But this is one of the first results we proved, that the lexicographically least A over B power-free word is the lexicographically least A power-free word. And just to show you one direction of the proof, it's pretty simple. The other direction is a little bit more complicated, but not too much more complicated. So if we have an A power, B to the A,